Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951866602. I'm studying in CSE, AI, and ML, that is Computer Science and Engineering, the specialization of Artificial Intelligence and Machine Learning, 4th semester, Institute of Aeronautical Engineering. In this Tech Talk video of the subject of Database Management Systems, that is DBMS, the topic I'm going to speak upon is Advances in Automotive Radar, a framework on computationally efficient high-resolution frequency estimation. So let's dive into the topic. First of all, let's go through the contents. In the first place, I'm going to introduce the concept of automotive radar data. There will be understanding the data landscape of modern radar systems. Next, I'll be explaining the challenges of real-time radar data management, the real-time processing requirements and storage constraints, and then high-resolution frequency data characteristics, high-dimensional time-dependent signal properties. Then I'm going to explain about efficient estimation network, the computational optimization and memory reduction strategies involved. Then I'll be explaining about database modeling and query optimization, schema design, performance enhancing techniques, and the key schema components and every query, the query optimization strategies. Then I'll be discussing about query processing and optimization techniques, the optimization techniques that collectively ensure sub-millisecond query response times. Then I'll be explaining the performance impact of database optimization, that is the graph representation of optimization and quantifiable benefits. And after that, in the final piece, I'm going to conclude the topic with an overall summary. So let's go through the first content. Introduction to automotive radar data. Modern vehicles continuously generate massive volumes of radar sensor data, forming the foundation of advanced driver assistant systems (ADAS) and autonomous navigation. Automotive radar systems rely on precise frequency estimation algorithms to detect objects, measure distances, and calculate velocities in real time. High-resolution frequency estimation significantly improves safety-critical functions such as collision avoidance, adaptive cruise control, and lane-keeping assistance. But however, this precision comes at a cost: the generation of complex high-volume datasets that demand sophisticated management strategies. Database management systems play an increasingly crucial role in storing, organizing, and processing this data efficiently whilst managing the low latency requirements essential for vehicular safety applications. Hence, that was the introduction. And now let's go through the challenge of real-time data management. Here we have to discuss about three main aspects. Continuous data streams. Radar sensors produce real-time streaming data at rates exceeding several megabytes per second, creating sustained pressure on storage subsystems and network infrastructures. Storage overhead challenges. Large data volumes accumulate rapidly, leading to significant storage overhead that impacts both cost efficiency and data lifestyle management strategies. Retrieval latency constraints. Inefficient data handling introduces retrieval latency that can delay critical safety decisions, potentially compromising vehicle and passenger safety. So database management systems address these challenges through structured storage architectures, fast access mechanisms, and robust data consistency protocols, all essential for real-time automotive applications where milliseconds completely and compulsorily matter. Hence, that was all about everything about the challenge of real-time radar data management. Now let's go through high resolution frequency data characteristics. Here we have to discuss about data properties. The radar frequency data exhibits unique characteristics that distinguish it from conventional sensor data. One of the characteristics are high dimension that the data is high dimensional. The radar frequency data, it is high dimensional, that is multiple frequency components per measurement occur, and it is time dependent temp because temporal correlation access across successive samples is present, and it is continuously updated. Streaming data requires incremental processing. Closely spaced components requires precise numerical representation. And after this, on this basis, we have database requirements. These properties impose specific demands on database architecture. One of those is temporal query support, time range filtering and windowing options. The next one is range-based searches, frequency band queries for object classification, pattern analysis capabilities, detection of recurring signatures, optimized schemas, tailored data models for radar-specific access patterns. Addressing these requirements demands careful consideration during database schema design and index selection. Since that was all about high resolution frequency data characteristics. Now let's discuss about efficient estimation framework. Here we have three main aspects to discuss about. First one is algorithm optimization. Advanced preprocessing algorithms reduce computational cost and memory usage using initial signal processing stages. Feature selection. Only relevant frequency features are extracted and retained, eliminating noise and redundant information before storage. Database integration. Reduced data volumes enable scalable real-time database operations with minimal latency impact. This framework establishes a crucial preprocessing layer that bridges computationally intensive signal processing with efficient database operations. By reducing data redundancy before database insertion, the system achieves substantial improvements in both storage efficiency and query response times, enabling real-time performance even under high sensor data rates, or whatever we call it. Hence, this was all about efficient estimation framework. Now let's go through database modeling radar frequency data. Database modeling for radar frequency data. Here, for modeling the database, we have to address through three main components. First one is relational tables. Next one is time series databases. Next, sensor schemas. These form a database in which multiple modeling paradigms can effectively represent radar frequency data, each offering distinct advantages, due to which here we come across through the components of the key schema. There are three main components: timestamp, that is high precision temporal markers with nanosecond resolution; frequency values, multi-dimensional arrays representing spectral content; and close identifiers, the unique tracking references for detected agents. Then we have optimization strategies. We have three main strategies. Normalization. It eliminates data redundancy and update anomalies. Strategic indexing. B-tree and hash indices on frequently queried attributes. Partitioning. Temporal or spatial data distribution for parallel access. Hence, that was all about database modeling for radar frequency data. Now let's discuss about query processing and optimization techniques. We have four main techniques. First one is multi-dimensional indexing. Compound indices on frequency and time attributes accelerate range queries and temporal lookups, reducing scan overload by orders of magnitude. Query result caching. Frequently accessed query results are cached in memory, dramatically reducing repeated computation costs for common access patterns. Horizontal partitioning. Large datasets are partitioned by time windows or spatial zones, enabling parallel query execution and improved input-output performance. Materialized views. Pre Pre-computed aggregations support rapid analytical queries for object tracking, speed estimation, and event detection applications. These optimization techniques collectively ensure sub-millisecond query response times, meeting the stringent real-time requirements of automotive safety systems. Hence, that was all about query processing and optimization techniques. Now let's discuss about performance impact of database optimization. Here, if you look at the graph representation of optimization, the data before optimization is initially very low, but the data after optimization is very high. That is the value of optimization in database. We have quantifiable benefits. Implementing comprehensive database optimization strategies yields substantial performance improvements across critical metrics. We have 98% of reduction in average query latency, 67% of decrease in storage requirements, and 14 times more improvement in data throughput. These improvements directly translate into enhanced real-time responsiveness, reduced infrastructure costs, and improved scalability for production automotive systems handling multiple concurrent data sensors. Hence, that was all about performance impact of database optimization. And now finally, I would like to conclude the topic. Hence, advances in automotive radar systems rely not only on sophisticated signal processing algorithms, but also on robust database management frameworks that enable efficient storage, retrieval, and analysis of high-resolution frequency data. By systematically applying database management concepts, including optimized data modeling, strategic indexing, horizontal partitioning, and intelligent query caching, high-resolution frequency estimation data can be stored and processed with the efficiency and low latency demanded by real-time intelligent vehicle operations. This integrated approach bridges the gap between computational signal processing and scalable data architecture, establishing the foundation for next-generation autonomous driving systems that are both reliable and performant at scale. Hence, this was the entire topic. And finally, I would like to thank the respected professor for giving me this wonderful opportunity to speak upon this wonderful topic. Thank you.